In section 311, we are going to discuss related rates. And what this means is that when we have an equation where one value is dependent upon other values, that means that their rates of change are also going to be related. So think of any formulas where one value is dependent upon other, like area formulas or perimeter formulas. The Pythagorean theorem, where the hypotenuse is dependent upon the two legs. Trigonometry formulas, where the sine of an angle is dependent upon the opposite and hypotenuse of a triangle. So any formula that you've ever worked with, we have one value that's dependent upon another or possibly several other values. If we were to go through and take the derivatives of everything in those formulas, we would have a new formula that would relate all of their rates of change to one another. So anytime we talk about rate, usually it's with respect to time. So we're going to be almost exclusively differentiating with respect to time here. So one example just to consider, like for area of a square. The formula for area of a square is just side squared, because the two sides of a square have the same length. So the area of a square is dependent upon the side length. So with rates, we are going to differentiate with respect to time, because we want to know how slowly or how quickly something is changing over time. That is always what rate is referring to, how fast or how slow. So if I know how to calculate area based on side, I can also figure out, by taking the derivative with respect to t, how a change in the side length will affect the change in the area, or how slowly or quickly that side length changes could affect how slowly or quickly the area changes. So you can imagine this square growing or shrinking and making a larger or smaller square, and this little change in s here, delta s, is going to create a change in area, delta A. And the last time we saw deltas is when we were talking about derivatives in our formal definition of derivative. So we want to know tiny little changes in one value, how it's going to affect changes in the other value, specifically with respect to time. So one of the things we said that derivative could represent is rate of change. And we have said that several times, along with slope, tangent slope specifically. So we're just going to be using derivatives here again, but more specifically derivative with respect to t, because they're going to be rates. So I want to show you an example with that square. Let's suppose that the side length of a square is increasing at a rate of 2 centimeters per second. Determine the rate of change in the area when the side length is 10 centimeters. So there's a couple of things you should always look for when you see these rate of change problems. Some of the values they give you will be static values, and what that means is values that are not changing values. They're not rate values. They're just a value for the variable at one specific point in time. And then some of the values are going to be rate values. They're going to be derivative values. And the way that you can tell is because they have a time unit in them. So this is one of them, 2 centimeters per second. This is telling us that the side length of a square is increasing at a rate of 2 centimeters per second. Now, centimeters is a linear unit and seconds is a time unit. So that tells me that that is the derivative. That is a derivative. And we talked about this a few sections ago, that if down here our sides are measured in centimeters, then a derivative with respect to time, we could, since time is in the denominator, that would put a time unit in the denominator of our new value that we're calculating. So in this problem, they're talking about area and they're talking about side lengths for a square. So those are that's important to point out right away, because that's going to tell us the formula that we need to use. So we know we need to use area equals side squared. And then they want us to figure out the rate of change in the area. So that tells me I need to differentiate with respect to t. Now this is going to be an implicit derivative. Anytime you are taking a derivative of a variable that does not match the derivative in, or the variable in the problem, it's considered an implicit derivative. And that means you can apply your normal derivative rules to the variable, but then you also have to put that extra chain rule piece after it, like we did with the dy dx back in our implicit section. So the way that this implicit derivative is going to look is, well, the derivative of a is just a linear variable. So its derivative is going to be 1. But because a and t don't match, we would also say, because of the chain rule, dA dt. And then for s squared, we're going to do the power rule. So it's going to be 2s to the first. And because s and t don't match, we would also say ds dt. Now I'm going to clean this up a little bit, because algebraically we don't need the times 1 in the front. We can just say dA dt. And then we also don't need a power of 1. So we can say 2s ds dt. So with our implicit derivatives, anytime you're taking the derivative of a variable that doesn't match your derivative there in the denominator, you're going to you're going to work it implicitly, where you do normal derivative rules and then also that extra chain rule piece afterwards. So this is the formula that tells us how their rates of change are related. And now we can use some of the values they gave us. They said find dA dt, find the rate of change in the area, which is dA dt. If the side length is increasing at a rate of 2 centimeters per second, that is ds dt. When the side length is 10, that is our static value, that's just s, which is 10. So this is in centimeters, this is in centimeters per second. And if we multiply all of that out, we get 40 centimeters squared per second. So our area is changing by 40 centimeters squared every second at that exact moment that the square has a side length of 10 centimeters. So you can imagine, you can try to imagine, or I can try to do it here with a little picture. We've got this square that's just getting bigger and bigger and bigger and bigger, and what we're doing is we're just measuring how the side length is getting bigger, but also at the same time the area is getting bigger. So it starts off small, and the side length is continuously getting bigger by 2 centimeters per second. So here s equals 10, and then it's also expanding. ds dt is 2 centimeters per second. It is expanding by 2 centimeters every second. We want to know how area is expanding, dA dt. And that's what we just figured out. The area is going to expand by 40 square centimeters every second in this scenario. So for the next exercise is very similar, but I wanted to show you that it doesn't only work for things that are getting larger, but it also works for things that are getting smaller. So we might have to use negatives to represent things getting smaller. So in this example, it says a circle has an initial radius of 50 feet when the radius begins decreasing at a rate of 2 feet per minute. So something you should notice right away is that it talks about the radius decreasing at a rate of 2 feet per minute. Because it says that it's a rate and the unit is feet per minute, that value is dr dt, because it's radius and it's a rate that radius is changing. And because it's decreasing, I'm going to say it's -2 because it's decreasing. So dr dt is -2 feet per minute. What is the rate of change of the area? So they want to know how area is changing, the rate of change of the area. They're asking us to find dA dt. At the instant, the radius is 10 feet. So when r is 10. It looks like that this information at the very beginning is unneeded, that the initial radius is 50 feet, that it's just there to throw us off and is completely useless. So they're talking about the relationship between the radius and the area for a circle. So the formula we're going to need is the area formula for a circle, which is pi r squared. Now to get the related rates formula, we need to differentiate with respect to t, which is an implicit derivative. So this is going to give us dA dt equals 2 pi r, that's our power rule on the r, and then dr dt, because the r and the t don't match, so we always add that extra piece anytime those variables don't match. This is our related rates formula. This is how the rate of r changing is related to the rate of a changing. And we know a few of these values, so we can plug them in. We know that dr dt is -2, and we know that r is 10. Pi is just a constant, 2 is just a constant. So really, we know everything on the right-hand side here, and we can solve for dA dt. So that 10, and I'm going to use some units here, the 10 was in feet. And then dr dt was -2 feet per minute. And if we multiply this all out, we can keep it as an exact number with a pi in there, or we can type it in our calculator and get an approximate. This is going to be -40 pi square feet per minute. Or if we go ahead and multiply that pi in, it's going to be about -125.7 square feet per minute. Now, this radius is really important because the current size of the circle is going to affect how area is changing. If you look at a really small circle and you change it by just a tiny bit, then we're talking about this area. That's the change in the area. If we're talking about a really big circle and we change the radius by the same exact amount, so that thickness is exactly the same, but now we're talking about this area. Now, the change in the radius is exactly the same, but the initial radius was different. Now, that blue area is a whole lot bigger than the red area. So this one is a much smaller radius. So that's a little r. This radius is a much bigger radius, so big R. But the change in the radius is different, or is the same on both of them. So the value of the r is really important. You don't just need how the radius is changing to get how the area is changing. It's also very dependent upon what the current radius is as well, as you can see from this example. A really small circle makes a really small ring of extra area. A really big circle makes a much bigger ring of extra area. So we're going to do a couple more that get a little bit more difficult. And I know this next one, you've got one similar to in your homework. And it's talking about piston compression. It says a piston is seated at the top of a cylindrical chamber with a radius of 5 centimeters. So I'm going to go ahead and write that down for now. We may need it, we may not. We'll see. When it starts moving into the chamber at a constant speed of 3 centimeters per second. So the piston is moving down. So that is the height of the cylinder. And the height is changing. The height is decreasing by 3 centimeters per second. So I'm going to say dh dt is negative 3 centimeters per second. What is the rate of change of the volume of the cylinder when the piston is 2 centimeters from the base of the chamber? So when h is 2. So what is the rate of change of the volume? Rate of change of volume. So they're asking us to find dv dt. Now this R value is never going to change. The radius on this piston is always 5. But the height is changing. So we need to be careful about what values we plug in right away and what values we have to plug in at the end. The volume for a cylinder is pi r squared h. Now this section uses lots of different formulas, and I don't want you to stress about that when it comes to test time. You would be given the formula that you need for any related rates problems on the test. Well, I just want you to be concerned with how to solve a related rates problem and not be stressing yourself over, oh my gosh, I've got to memorize 50 different formulas because I don't know what kind she's going to give me. I will give you the formula that you need for the problem. You just worry about being able to actually solve the calculus part of it. So volume of a cylinder is pi r squared h. Now that radius never changes. The radius of that piston is always 5 centimeters. So because it never changes, we can go ahead and plug it in right away. Height is changing, and we have a dh dt value, so we can't plug them in right now. We've got to wait until after the derivative. But I can plug in my r, so I can plug that 5 in, and 5 squared is 25. So really, our volume formula is going to be 25 pi h. It's only the height value that is changing in this piston, because that piston is going up and down, but the radius is not changing. So to get the related rates formula for how height and volume change with respect to one another, we are going to differentiate with respect to t. And when we do that, we get dv dt equals, and now on the right hand side, h is just a linear variable, which means that the derivative is 25 pi. It's just its coefficient. And then we also need to do our chain rule that says we have to multiply by dh dt. So we really don't need that h is equal to 2, because there's no h's left in the related rates formula. But we do need that dh dt value that they gave us. So dv dt, that's the rate at which the volume is changing, is 25 pi times our dv dt, or our dh dt, how our height is changing, which is negative 3 centimeters per second. And in order to get our units right, we need to know that this 25 here in the front was centimeters squared, because that was our radius squared. So dv dt, which is how our volume is changing over time, is going to be negative 3 times 25, which is negative 75 pi cubic centimeters per second. And that would be our exact value If we wanted an approximate value, we could go to our calculator and actually see what negative 75 times pi is. And I've got about negative 235.6. So this would be our exact answer. If we were asked to leave it exact, this would be our approximate to the nearest tenth, if we were told that we could round it to the nearest tenth. So this is a good example of where we actually have two variables. Volume is dependent upon radius and height, but we can go ahead and plug radius in right away because radius never changes. Radius is a constant value, so we don't have to worry about there being a dr dt value. We can plug that 5 in right away and just worry about the relationship between dv dt and dh dt. It's just volume and height that are changing. The next example is a classic related rates problem. Anybody who has ever taken calculus before has seen this type of problem with this sliding ladder against a wall. So it says we've got a ladder against a wall. It is a 13-foot ladder. So this hypotenuse, we see this triangle here. The hypotenuse of the triangle is 13. A 13-foot ladder is leaning against a vertical wall. When Jack begins pulling the foot of the ladder away from the wall, so he's doing this, at a rate of 0.5 feet per second, how fast is the top of the ladder sliding down the wall when the foot of the ladder is 5 feet from the wall? So if we're going to pull the bottom out, that is simultaneously going to pull the top down. And we know how fast the bottom's being pulled out, and we want to know how that's going to affect the top coming down. So there's two different variables here, and we need to label them. And I'm just going to call them X and Y since one's horizontal and one's vertical. And the relationship between these three sides, we can use the Pythagorean theorem for that because they're three sides of a right triangle. So the formula I'm going to set up is x squared plus y squared equals 13 squared, or x squared plus y squared equals 169. Because no matter where that ladder is situated, it's always going to make a right triangle with the wall. So based on what I've labeled, I'm going to go back into my problem now and label some of these numbers. So a 13-foot ladder, we've already used our 13, is leaning against a vertical wall when Jack begins pulling the foot of the ladder away from the wall. So he's pulling the foot of the ladder away from the wall. That means the x distance is getting larger by 0.5 feet per second. That is dx dt. I know two ways because it says rate and it's per second. So dx dt equals 0.5 feet per second. How fast is the top of the ladder sliding down the wall? So they're talking how fast, so that is a rate. They want to know dy dt. When the foot of the ladder is 5 feet from the wall. So the foot of the ladder is the bottom horizontal piece. So x equals 5. So I'm doing a lot of problems, but they all have their own little kind of twist to them, and this is no exception. There's going to be an extra little twist to this that we have not seen yet, and you probably don't know it yet, and you won't know it until we get to it. So just like the other ones, we need to go ahead and differentiate everything with respect to t. So I can do the power rule on my x squared, and I get 2x. And then remember, it's implicit, so dx dt. Power rule on the y squared is going to give me 2y, and it's implicit, so dy dt. And then the derivative of 169, it's just a constant, so the derivative is 0. And then if you look back at the information that we have, we know dx dt, we know x, so we know dx dt, we know x, we want to find dy dt, we don't know y. Y is in this equation, and we don't know it, and we can't solve it until we know it. But luckily, this formula here gives us the relationship between x and y. So we can figure out y really quick. We didn't necessarily know when we started this that we would need it, but now that I see my related rates formula, I can see that I need it. So I'm going to go back up here to x squared plus y squared equals 169, and I'm going to plug in my x equals 5 and solve for the y value, because I see now that I need my y value. So 25 plus y squared equals 169. So I can subtract my 25 over. I get y squared is 144, which means y equals 12. So perfect. We know our y value. So we're ready to go ahead and plug into our related rates formula. 2 times 5 feet times, we know dx dt was 1/2 foot per second, plus 2 times 12 feet times dy dt equals 0. And we need to solve this equation for dy dt. So we can multiply all these guys together, and this ends up as 5 square feet per second plus 24 feet dy dt equals 0. I'm going to subtract my 5 over. I get 24 feet dy dt equals -5 square feet per second. And then I can divide my 24 feet over. We get dy dt equals, and one of those feet units will cancel, -5/24 feet per second. Now the negative just means that the top of our ladder is sliding down the wall. That y distance that we had drawn is getting smaller. So the x distance is getting larger and the y distance is getting smaller. So the trick on this one is that once we do our, once we go through and we differentiate with respect to t, we realize that we don't have all of the values we need, but we can always go back to this original equation and get any values that are missing so that we can keep going. So I'm going to do a couple more. This next one is pretty tricky. And I know you have one similar to this in your homework as well. So I want to make sure I did one like this. We are draining a conical tank. It says an inverted conical water tank with a height of 12 feet. So I'm going to start writing down some of our values. H equals 12 feet. and a radius of 6 feet is drained through a hole in the vertex at a rate of 2 cubic feet per second. Now, it is a rate because it's per second. It says rate, but you need to be really careful about what this is the rate of. And the key is to look at the unit in the numerator. So what is measured in cubic feet? So think about what you can measure in cubic feet. Volume gets measured in cubic feet. So dV dt is volume is leaving the tank at 2 cubic feet per second. So we could say -2 feet cubed per second. What is the rate of change of the water depth? So that is going to be dH dt. When the water depth is 3 feet. And they give us a hint. They say use similar triangles. And the reason they're giving us this hint is because of the formula for volume of a cone. That formula uses height and radius. And if you imagine what is happening as the water goes down, the height is changing and the radius is changing. So we can't replace either one of these values at the beginning. What we can do, though, is use similar triangles because the ratio between the height and the radius is always going to be the same all the way down. So I can replace one of them with an expression that's always going to be true all the way down. The height is always going to be double the radius. So when we get halfway down and height is 6, we will have a radius here of 3. And right here, when height is 3, radius will be 1.5. That relationship between height and radius inside the cone will always be true. So height is always going to be double the radius. And we can use that to replace one of the variables in our volume equation. That way we're not having to deal with two variables when we do derivatives, especially because they did not give us a rate of change for the radius. Even though we could probably come up with a rate of change for the radius, it'd be a lot trickier. Also, because technically you can't do derivatives yet when there are multiple variables. That's actually calculus 3. We can only do derivatives when there is one variable on each side of the problem. So we need the formula for volume of a cone. So let's see what that is. Formula for volume of a cone is 1/3 pi r squared h. Volume of a cone is 1/3 pi r squared h. We know that h, our height, is always double the radius, but technically we want to keep height in the problem. I don't want to replace height with 2 radius. Then my formula would be in terms of v and r. I want my formula in terms of h and r because I'm trying to solve for dH dt and I have an h. Now these two were only given to us so that we can establish this relationship. Those were just like the initial specifications for our cone. We're not actually going to use those when we solve. So really, I want to divide that 2 over to the other side and say that R is always going to be 1/2 H. And I'm going to use that to replace R in my formula. So then I can have a volume formula that's all in terms of H. So volume is 1/3 times pi times 1/2 of H squared times H. So instead of R, I put 1/2 H. And we'll do a little bit of simplifying here. A half squared is 1/4, and then 1/4 times 1/3 is 1/12. So volume is 1/12 pi, and then H squared, and then another H is H cubed. So 1/12 pi H cubed is going to be the volume for this particular cylinder. And we will go through and differentiate everything with respect to T. And we get dV dt equals, now 1/12 pi is just a coefficient. And we'll do the power rule on the H cubed. So we bring down the 3 and we get H squared. And then chain rule says we have to also do dH dt. Now the 3 and the 12 can simplify to 1/4. And we've got some values we know we can plug in. We're told that dV dt is -2 cubic feet per second. We also are interested in what is happening in particular when height is 3 feet. So we can plug in H equals 3. And we're trying to solve for dH dt. What is the rate of change of the depth? Like if we were just standing there watching this water drain out of the cone, how quickly would we see the depth of the water be falling? So we want to multiply all this stuff together and then divide it over. So 1/4 times pi times, well, 3 squared is 9, so that's 9 pi over 4 square feet times dH dt. And then I'll divide that 9 pi over 4 square feet to the other side. So we're going to do -2 divided by parentheses 9 pi over 4. And I've got -0.283 approximately. And 2 of those square feet will cancel with 2 of those. So it came out negative because we are draining this this cone. So the depth of the water is falling. That's what the negative means. So the depth of the water is falling by 0.283 feet per second.